So, did you look at this example? Let's take a look at it. Let's go ahead and finish it. So, if you add these together, solve by elimination. If we do, so we call this equation 1, equation 2. So, if I do 3 times equation 1, I get 9x minus 3y equal to 6. And then I still have the negative 9x plus 3y equal to 4. And then if I add together, you get 0, because everything there is going to annihilate each other, cancel out. So that's 0, that's 0. And so you get 0 equals 10, which 0 equals 10, which is a false statement. So anytime you get a false statement, you're done. You can just say that's it, no solution. So therefore, no solution. And just consistent, inconsistent, we say the system is inconsistent. And the equations are independent. Okay, so dependent means it's the same line. All right, so that wraps up that example. Let's go on to the next section. We'll spend a little bit of time on this, but we really want to focus mostly on solving system by matrices in chapter 6. But this will at least get us started. So 5.2. Excuse me, systems of linear equations in 3 variables. So systems of linear equations in 3 variables. So linear equation in 3 variables looks like this. AX plus BY plus CZ equal to D, where A, B, C, and D are just real numbers, constants. So what that creates, so the solution to that type of system is an ordered triple, X, Y, Z, called an ordered triple. So it's a solution in space. And I'm going to go ahead and draw this 3-dimensional axis system, although you won't really have to do this because we're not going to really look at this so much, but just know what it looks like. So in the classroom, what I usually do is look at the corner of a room, like right where the front board has that tray and it meets the corner of the room, and then the vertical axis is the z-axis. I wrote that wrong. Vertical axis is the z-axis, and one direction is x, one direction is y. And so an ordered triple in space, you go out however many along the x-axis, and then the y. And so down here it would be an ordered pair, but then you go up to the point in space along your z. So that's your x, y, and your z. So it looks kind of like that. So that's your ordered triple x, y, z in space. And then you have octants, right? It's 8 different regions that are octants. What we need to know, though, and visualize, and you need to look at the book and or use other online stuff, is we need to know what this is. This is basically a plane. So that represents a plane in space. So we can draw a plane, and then this is just for illustration for the notes, not something you have to do. So if you do a XYZ again, like this, you can draw a plane by putting these 3 dots that where it intersects the axes. So you get this sort of looking thing. but it goes off indefinitely in all directions. So that's your plane like that, but it of course goes off out here and everywhere. So just look around the room, your computer, your desk, your ceiling, all those are planes that go out, and you picture those going off to infinity, approaching infinity. So that's what they represent. So question then is, how many different planes do you need so that the intersection is one point? All right, so how many different planes do you need so the intersection is one point? Well, if you have two planes, they're either parallel, right? You either have parallel planes where they just don't intersect at all, like this. So these I'll try to draw these parallel. Right, so you have parallel planes are either like this, and those may not intersect, or you're going to have a plane, and then the intersection is going to come down like this. Let's see. It's going to come down and intersect in a line. So this might be another plane, and that intersection's a line. So you need three planes. You need another plane, all right, to come down and intersect at one point. So look at three different planes in the room. Just take the back wall, front wall, side wall, and you'll see that the intersection is a point. Just take the ceiling, right? And then that's your point of intersection. So we need three equations and three unknowns. So that's the concept. Three equations and three unknowns may give us what we say a unique solution. Unique being one. So one solution. So you'll see basically then three of those equations, and then you solve by elimination. That's really what we'll be doing. So let's just go straight to an example, and we will simplify and solve. Oh, I almost forgot back here. This is called, in this form, this is standard form. So standard form looks like that. So first we're going to need to write everything in standard form. Is going to be the process of what we do. So let's look at this example. Solve the system by elimination. Pretty much only want to use elimination on these. So the system is 5x equal to 2y minus 3z minus 3, 4y equal to negative 1 minus 10x minus 5z, and 2z equal to 5x minus 6y. So that's my system. And so the first thing you want to do is write in standard form. All right, so you want to bring everything to the left-hand side, constant on the right-hand side, and put it in standard form. So try that. I'll give you a moment to try that. Well, pause it and try that, obviously. Okay, so standard form, we get 5x minus 2y plus 3z. And so always write it in that descending order, like x, y, z. You could see, and you may see in the book, the subscripts, x1, x2, x3 as subscripts. So basically those are the x, y, z. That equals to the negative 3. And then we have 10x plus 4y plus 5z equal to negative 1. And then minus 5x plus 6y plus 2z equal to, in this case there's no constant, so it's just going to be 0. So take a moment to double check that. Okay, so one of the key concepts here when you're eliminating a variable, so we want to eliminate a variable. So one of the key ideas then is you must use each equation at least once. So that's kind of your concept. So you're going to eliminate a variable, then you got to do it again so that you use each equation once. So for here, what equation might we want to eliminate? What could you add together the equations and eliminate? And yes, you can see equation 1 and equation 3. If we add those, you get to eliminate the x. So let's do that. So I'm going to call this equation 1, equation 2, and equation 3 in that order so I can say what I'm doing. And this is important for future stuff for matrices. So I'm going to do equation 1 plus equation 2 and then write it right there. So I'm going to add those together and I get 4y plus 5z equal to negative 3. So I've just eliminated the x. Okay, so now let's do the same thing. You got to use the equation you didn't use yet. So that's equation 2. So equation 2, you have a 10 and a negative 5. So you got to use this equation and then one of the others, equation 1 or 3. So what I did is equation 3 and 2. So equation 3 and equation 2. So if I do 2 times equation 3 and add it to equation 2, what will happen? Will I eliminate x? Yes. So write down what you're saying, what you're doing. You're going to do 2 times equation 3 plus equation 2. So when I do that, 2 times equation 3, I get that's 0. And then this 2 times 6 is your 12. So I get 16 y plus 9z equal to negative 1. So that's my new system. So now we need to eliminate again. So now you just reduce this down to 2 equations, 2 unknowns. So we can eliminate z or y. So let's just, what looks easiest to me, probably y, because you only have to multiply by one constant. So let's just do that. So let's do, what should it be? How do you eliminate y? So yes, it's going to be negative 4 times equation 1 to give you that negative 16. And then you're going to add equation 2. And so you get negative 11z. Do this arithmetic off to the side. I'm just showing you so I don't spend too much time when you can do it on your own, some of that arithmetic step. And then you solve that, and you get z is equal to negative 1. Right, so from there you back substitute. That's what we call it. So back substitute into the previous equations. So you may use either of these 2 equations. So you use this one or this one. And then you solve for your y, and then you back substitute to either the original equation 1, 2, or 3 to solve for your x. So the idea is you go back to here and then you go back to here. So that's the concept. Okay. So I picked equation 1. So you get 4y plus 5 times negative 1 equal to negative 3. And then you continue to solve that for your y. So you get 4y. That's a 5. So 5 minus 3. Continue to solve. So y is equal to 1/2. Okay, then back substitute these two. So now you're going to take 1/2 and negative 1 and substitute into either of those. You could go back to the original, but you don't really have to. Okay, so you want to go back to where you see x in your system. Okay, so I used equation 3 for no particular good reason. Maybe because there's a 0 there on the constant, make it a little easier. So I used equation 3. So it's negative 5x plus 6 times 1/2, which is your y, plus 2 times negative 1 equal to 0. Then you just simplify that. So negative 5x plus 3 minus 2. So it looks like 1/5. That's equal to 0. Continue to solve. So that's a 1. So positive 1/5. So it's negative 5. I'll come back down here. So negative 5x equal to negative 1. So x is equal to a positive 1/5. So that's your unique solution because you get an ordered triple. So it's x, y, z. So your x is 1/5. Your y is 1/2. And your z is negative 1. Okay, so there's your solution, and that is what we call a unique solution. Okay, let's continue. Let's do an application. So we're going to do an application. I'm going to grab the question in my little holding thing here. So here's the question. I'm just going to copy that and bring it back. Okay, so we're going to paste that here, and here's the question. This is number 44 from the book. All right, so let's take a look at this question. So, and let me go ahead and erase some of this stuff, right? Because I had that for description purposes, and we'll do it over again. So, a theater charges $50 per ticket for seats in section A, $30 per ticket for seats in section B, and $20 per ticket for seats in section C. For one play, 4,000 tickets were sold for a total of $120,000 in revenue. So that's one information, right, that you can use. The next piece of information is 1,000 more tickets in section B were sold than the other two combined. How many tickets were sold? So we need first set up our variables and then figure out your equations. So your tip-off here is that you have the sections. So you have section A, B, and C. So you have maybe two things right off the bat. The first thing is the number of tickets. Okay, so the number total of tickets. That's the easy part. And the second thing you have that's kind of easier is the revenue. So revenue is always the number of something times the cost, right? Revenue is the number of things you sold times the cost or the price, right? So, and you have the prices. You have 50 for A, 30 for B, and 20 for C. So we need variables first. We need to define our variables. So it's the first thing you want to do that's kind of part of the work is define the variables. So we're going to let A, B, and C be the number of tickets sold in each section respectively. So let A, B, and C. And you could choose any variables. I just wanted to match. It's just easier for me. You could choose X, Y, and Z. B, the number of, so number of tickets sold in sections A, B, and C respectively. So they match up, right? So if they're the number of tickets sold, then we know that the number of tickets total was 4,000. So A plus B, number of tickets in A plus the number of tickets in B plus the number of tickets in C must equal 4,000. So that's your first equation. So how many variables? There's 3 variables, right? How many equations do we need to solve the system? Okay, and that goes back to what we just talked about. You need 3 equations. Okay, so going back to here, you have 3 equations, 3 unknowns. So this is your concept you have to understand, you have to know. So then the next one is revenue. So if you do multiply A, B, and C by the cost, you get your revenue. So it was $50 times A plus $30 times B plus $20 times C. And then what was the revenue? The revenue is right here. The revenue is 120. So the revenue is 120,000. Okay, so that's your first 2 equations, somewhat easier than the next piece. The next thing is saying there are 1,000 more tickets in section B were sold than the other 2 combined. So we're comparing, let's do this over here. Do this little scratch work over here. So we are comparing 1,000 more in section B. So we're comparing B and then the other 2 combined. The other 2 combined would be A and C. All right, so which side gets the $1,000? So think about this. Do you put, so there's $1,000, not dollars, I mean 1,000 number of tickets. Do I put 1,000 here or do I put 1,000 here? Okay, so which is it? So 1,000 more tickets were sold in section B than the other 2 combined. So how would you balance the equation, in other words? And so to have this equation balanced, think of it like that, like a balancing thing here. Oops, I didn't write that very well. So you get, so 1,000 more in B than the other 2 combined. So where do I put the 1,000? 1,000 has to be over here because B is more, there's more B's. So to balance the equation, 1,000 has to be on the right-hand side. So B is equal to A plus C plus 1,000. So that's your third equation. So B equal to A plus C plus 1,000. So that's your system that you want to solve. So the first thing you want to do is write that in standard form. So standard form is A plus B plus C equal to 4,000. And this next part is standard form, but I went ahead and divided out by 10. So because it just makes it simpler. So 5a plus 3b plus 2c equal to, and then so then it's 12,000. Okay, so you can divide by 10 because there's a 10 in common. Make that a little easier. And then you need to bring over your a, so it's negative a plus b minus c equal to 1,000. All right, so that's the system you want to solve. Okay, so pause the video and take a moment to solve that. Again, put it in standard form and then use elimination to solve. Okay, so pause that, try it. So when you solve it, you should get A is 500. B, you should get 2,500. And C, you should get 1,000. So there were 500 tickets sold in section A, 2,500 in section B, and 1,000 in section C. And you can, how could you check that? You can check that by adding them up. The total should be what? Total should be 4,000. Right, so you can check that pretty easily, and it looks like it works. And you can check, so you can check each equation to make sure it's working out nicely. Okay, let's go ahead and do another question. I'm going to go and grab the question from the notes. So I have some notes over here. Let's go and grab that. Copy that and come back. And then put it here. Okay, so next example. So try this one on your own and see how we do on it. I'm going to go ahead and erase some of this stuff again. Okay, so try it. I'll read it. Go ahead and pause it and try it on your own, and then I'll write it up. So a sawmill cuts boards of lumber for a lumber supplier. When saws A, B, and C all work for 6 hours, they cut 7,200 linear feet of lumber. Okay, so that's one thing. It would take saws A and B working together 9.6 hours to cut 7,200 feet of lumber. Saws B and C can cut that number, 7,200 of lumber, in 9 hours. Find the rate in feet per hour that each saw can cut. So you're finding A, B, and C. All right, so try that one if you haven't already. So let's got to define your variable. So you let A, B, and C be the rate of work for each saw, right, respectively, in feet per hour. Okay, so now we got to set up our equations. So working together, they have, so if they work for 6 hours, they cut 7,200. So they all work for 6 hours, you get, let's see, you get 6A, so 6A plus 6B plus 6C equals 7,200. All right, so if you can divide out by a common factor, should simplify a little bit. Okay, so then that's if they're all working, right? So the rate of work it takes 6 hours to do it, and you'll get that many linear feet cut. Okay, so now, what about the other two? Okay, so the other two would be 9.6 hours times A plus the 9.6B, and then that would give you your 7,200. Okay. Now, what about the 9 hours? So that's for saws B and C. So saws B and C would be 9B plus 9C. And that would give you your 7,200, 7,200. So what it equals is always going to be the same. It's just they're all working at different rates. It tells you how long they work for each one working together or not. Okay, so that's your system that you want to solve. Okay. Divide out common factors if you can. So divide common factors. So the numerator, in the first one, you have a 6 in common. It turns out 9.6 divides, and so does 9. So it actually works out rather nice for all of these. So you end up getting A plus B plus C equal to 1,200. You get A plus B equal to 750, and you get B plus C equal to 800. So you have that equation. So to solve this, use any method you want. When you're solving the application questions, it doesn't matter to me which method you use. In some ways, substitution is going to be kind of the easier way anyway. Okay, so let's see. So you have A plus. So using any of those equations, we can isolate and solve. So what might work best? Okay, so try that at this point. Okay, so try it. What you should get is A. Oops, that doesn't work. You should get A will be 400, and that's feet per hour. You get B is 350 feet per hour, and you'll get C is 450 feet per hour. Okay, so that wraps up this section. So focus on 3x3 systems and a few of these applications and just solving them. So there will be an application for sure on the test or final. When you get to this, though, you can solve any way you want, but I'll ask elimination or usually have it open. But we're going to focus more on this later in Chapter 6. So we're going to finish Chapter 5, and then Chapter 6 is when we use matrices to solve these